Today's lecture, we are going to continue our discussion on resonance. Last lecture, we looked at the basics of resonance, some rules to determine when we might have resonance, and drew some resonance structures. Today, we're going to look at the resonance structures in a little more detail, as well as continue to review our basic resonance theory. Okay, so let me draw a basic example here. If we have something like this. Okay, we have an oxygen, a couple carbons. We have this carbocation directly adjacent to this oxygen. Hopefully from last lecture, you should be able to understand that we can take this lone pair, since it's adjacent to a empty p orbital, carbocation, we can put this lone pair down here as a pi bond. And that means that those two electrons are in resonance, right? They're delocalized electrons that could either be a lone pair or they could be a p orbital bond, a pi bond, right? So if we put those two electrons down there, what would that look like? So we would have then this structure where we have a double bond at that position, right? We have a double bond there. We have one lone pair on oxygen, and now oxygen has a positive charge. So these would be two resonance structures of each other. These are the only two resonance structures we could draw for the molecule. Okay. So today we're going to look at these two molecules in more detail, these two resonance structures. We're going to determine which one has more impact on the overall electronics of the system. Remember, if we have multiple resonance structures, all of those resonance structures represent different ways that those delocalized electrons could be represented. And the actual molecule, in reality, is a sum of all of those resonance structures, right? So if we look at this example, these two electrons in red, right, they could be a lone pair, they could be a p bond, they could be a pi bond. And in actuality, it's both, right? These two electrons are both. They are found in the bonding area. They're also found in the lone pair area, right? So those two electrons are sort of in both locations. But when we have multiple resonance structures like this, one is a little bit better than the others typically. And some resonance structures we consider to be much less significant or even insignificant. Okay, so I'm going to draw out some rules that we can follow to determine sort of when is a resonance structure of high importance or of low importance. Okay, so let's put up here, I'll put rules for determining the importance of resonance structures. Okay, that's going to be the focus of the next couple of slides that I draw here. Okay, so rules for determining the importance of resonance structure. Rule number one, we are going to look for resonance structures that have as many filled octets as possible. Okay, so more filled octets means more significant. That means that resonance structure is of more importance. Okay, so the more filled octets, the better. So let's look at this example here. We have the two resonance structures above. In one case, we have a positive charge on a carbon. On one case, we have a positive charge on an oxygen. Now, the oxygen has a filled octet in both cases, right? It has 8 electrons around it in both cases. It just has a formal charge on the right, but it still has 8 shared electrons around it, right? If we look at the carbon, however, the carbon has a filled octet on the right, right? But on the left, we have a carbocation. We have a carbon that is electron deficient. It only has 6 shared electrons around it instead of 8. So therefore, based on rule number 1, if more filled octets means more significant, that means this structure on the right is a more significant resonance contributor than the structure on the left. So we'll put more significant, more significant on the right because everything has a filled octet. And on the left, we would put less significant, okay? Less significant again, because we have only 6 electrons around that carbon. That carbon does not have a filled octet. And based on rule number 1, the more filled octets we have, the better the resonance structure is, the more significant that resonance structure is. So in actuality, when this molecule exists, these red electrons are a little bit more favored based on rule number 1 in this area, in this pi bond area, right? They can still be up in the lone pair area, right? But based on rule number 1, based on these resonance structures, this structure on the right is a more accurate representation of the electron, of the electronics of the system. Okay. So there's rule number 1. More filled octets are better. Let's look at rule number 2 with an example. Let's draw a couple resonance structures for this molecule. Actually, that will be an NH there with a double bond. Okay, let me make that a little cleaner. Okay, so we have one carbon with an NH2 and an NH. We have a double bond there. So how can we draw a resonance structure of this? Well, we can take this lone pair and turn it into a pi bond. Remember, we're only dealing with lone pairs and pi bonds, okay? Single bonds all stay the same. And if we bring this down to make a pi bond here in the empty position, that means this pi bond needs to bump down, and it's at the end of a chain. So the only option we have is to turn it into a lone pair on nitrogen. So let's do that. That gives us H2N, no single bonds change. NH, now NH has 2 lone pairs, which will make it negative. This nitrogen over here has a double bond and 2 single bonds, so that's going to be a positive charge. And for a final resonance structure, we could bring that pi bond back to be a lone pair, and that would give us this structure over here just with single bonds. And then we have a negative charge on one side, and we have our positive charge on the carbon now. It's always a good rule of thumb to make sure your charge is balanced. You should have, if you start with 0 charge, a neutral molecule like we did, every resonance structure should be overall neutral, right? We have a plus minus, overall neutral. Okay, so rule number 2, when we're considering multiple resonance structures like this, we want as few formal charges as possible. Fewer formal charges means a more significant resonance contributor. Okay, that's rule number 2. So if we look at our 3 structures, we have a structure here with 0 formal charges. It's neutral. And then we have a resonance structure with 2 formal charges and with 2 formal charges. So therefore, based on rule number 2, fewer formal charges is better. That means our first resonance structure here that I circled is the major resonance contributor. Okay, this is another way you'll see this written. You'll see major contributor or minor contributors. So we'll call these, just based on rule number 2 here, minor contributors. They are minor contributors because they have 2 as opposed to 0 formal charges, and we want as few formal charges as possible. Okay. Now we could also look at these two minor contributors. Based on rule number 1, we could see that this structure over here has a carbocation that I circled. That carbon is electron deficient, so this is actually even more minor, right? If we combined rule 1 and 2. But once we go through all the rules, then we'll look at some examples where we combine all the rules and create a hierarchy for multiple structures. Okay, so rule number 2, the fewer formal charges, the better. Okay, pretty straightforward. Okay, let's draw this structure here. We have a ketone with a negative charge next door on this carbon. How can we draw a resonance structure of this? Well, remember, anytime we have a C double bond O, this polar double bond, we can draw a resonance structure where we put the pi bond up on oxygen on the more electronegative atom as a lone pair, which would give oxygen 3 lone pairs, a negative charge, a positive charge at the carbon, and then we still have this negative charge on this carbon over here with a lone pair. Okay. Another resonance structure we could draw, we could take this lone pair down here and turn it into a pi bond between the negative and the positive charge, right? So we could put that double bond down here instead. Now we have a -1 charge. We should have a -1 overall charge in all of our structures, and it looks like we do. Okay. So these would be 3 resonance structures we could draw. Now, based on this rule, what would be the best resonance structure? And that rule is rule number 3. A negative charge will prefer to be on a more electronegative atom. A negative charge will prefer to be on a more electronegative atom. Okay, so if we have these structures above, we will see in the first structure, we have a negative charge on carbon. On the third structure, we have a negative charge on oxygen. And the middle structure has a negative charge on both. It also has a positive charge. So this middle structure is quite bad. If we consider quickly the rules 1, 2, and 3, this is a bad structure because it has a carbocation. So it has, everything doesn't have a filled octet. So it breaks rule number 1, it goes against rule number 1. It has a lot of formal charges, so it goes against rule number 2. And it has negative charges on both oxygen and carbon. This is just a bad resonance structure. So we're going to just put insignificant. We're going to just call this an insignificant resonance contributor. Okay. Is it a possible resonance structure you could draw? Yes, but it's not very helpful. It has a lot of charges. It has a carbocation, and we have 2 better structures on the left and the right. Okay. Now, comparing the left and the right, they're very similar. The only difference is where that negative charge is. We have a negative charge. Everything has a filled octet. They both have 1 charge, right? So now what we have to do is we have to consider which atom is that negative charge on. And the negative charge is going to prefer to be on a more electronegative atom, oxygen, okay? So we will call this one the major resonance structure. And we'll call this one over here on the left the minor resonance structure. You could also call them more significant and less significant. I'm going to use the terms major and minor, just indicating that they both do have some contribution, but this one on the right over here is more of a major contributor to the overall electronics of the system. Okay, so rule number 3, negative charges would prefer to be on a more electronegative atom. And then finally, rule number 4, I'm going to draw here. Let's do it in black. Draw the carbonate ion. So we have a C double bond O. So this is the carbonate structure. If you think of sodium carbonate, you've probably heard of sodium bicarbonate, which is this structure, but with a hydrogen over here on the oxygen. This is a carbonate functional group. So I'm going to draw the carbonate anion, which is a dianion where we have two negative charges on these two oxygens. Okay. So there's the carbonate anion, CO3 2-. Maybe you know that from high school chemistry if you remember your polyatomic ions. Now let's draw a resonance structure here. Let's bring this lone pair down to be a pi bond, and we'll kick this pi bond up to be a lone pair. That'll give our first structure. This oxygen is untouched. Now we have a double bond down here and a single bond up here. Okay, that gives oxygen here, two lone pairs, two bonds, which is neutral. We have two negative, so the charges are balanced. That looks good. And then finally, we could bring this lone pair here to be a pi bond in the final location and kick that pi bond up to give our third structure. So we're essentially drawing that double bond in a different spot each time, right? We have a double bond on the top, the right, and then the left. Okay, so this is what it means to be in resonance, right? We have these delocalized electrons, and we could draw them as a bond in any location as a lone pair, right? So these delocalized electrons are sort of shared between all of these atoms. Okay, so we have all of our resonance structures drawn. Now we could, in theory, draw one more resonance structure where we break this bond and we put the electrons up on the oxygen in order to get this, but I'm not even going to draw that because it's insignificant based on all of our rules we discussed. It would look something like that. We have three negatives and a positive, so I'm not even going to bother with that. That would be an insignificant resonance structure, and we'll just consider these three resonance structures here. Okay. Okay, so we see these three resonance structures, and we see that they look very similar. They have similar characteristics. They both have two negative charges, both on oxygens. They all have two negative charges. They all have filled octets. Everything's the same. So what does that mean? It means that all of these are equal contributors. Okay, and that's rule number 4. Rule number 4 when all other things are equal, the structures are considered to be equal contributors. All other things equal, the structures are considered to be equal contributors. So these three, since all other things are equal, we would call these equal contributors. There's not a major and a minor contributor, but all three are equal. So that means that those delocalized electrons are all equally shared among all three oxygens. Okay. Again, we just can't really represent that with a pen and a paper, right? It's hard to represent that shared electron, the moving of electrons. So this is why resonance is important. We should be able to draw a structure and see from the structure, right? If I draw the carbonate anion up in the corner here, if I draw this structure, you should be able to just see by looking at it that there's resonance. There's a negative charge next to a double bond. So therefore, those electrons are shared. They're delocalized. Okay, so that's how you should start to think. Okay. Okay, let's get some practice drawing more resonance structures and ranking them based on their overall contribution, considering these 4 rules that we discussed. Okay. So for the rest of this lecture and then all of next lecture, we'll be doing a lot of practice. Lots of practice for resonance because it is a very tricky topic to initially grasp. Okay. Let's see here. Let's take this example. This is a good one. Let's start with this structure where we have NH2 and a C double bond O. This is an amide or an amide. And let's say the question asked to draw and rank all the resonance structures. Okay, let's do that. Draw and rank all the resonance structures for this molecule. Oxygen has 2 lone pairs, nitrogen has 1. We see we have a lone pair on nitrogen next to a pi bond. We also see we have a C double bond O, which is a polar pi bond between 2 atoms of differing electronegativity, right? So we can draw this first resonance structure where we just break that pi bond and put those electrons right up on the more electronegative oxygen. That gives us oxygen with 3 lone pairs, a negative charge, and then this carbocation here with a positive charge. Okay, now we have lone pairs on either side of this carbocation, so we could bring a lone pair down from oxygen like this, but that would just bring us back to our initial structure. So let's bring the lone pair from nitrogen down. That is going to give us a new structure where we have NH2 with a double bond, and then that single bond up to oxygen. NH2 with a double bond will be positive. Okay. And I believe that is all the resonance structures we could draw, right? If we move this pi bond back to nitrogen, that gives us our middle structure. If we bring those lone pairs down from oxygen to make a double bond and kick that pi bond away, that gives us our first structure. So these look like the 3 possible structures we could draw for this amide. Okay, so let's rank these resonance structures based on their overall contribution to the electronics of the system. So let's consider our 4 rules. The first rule, we have to consider, does everything have a filled octet? Okay, does everything have a filled octet? In this case on the left, that's good. Put a check mark there because that has all filled octets. The middle structure does not. We have a carbocation there. That's 6 electrons. That carbon in the center does not have 8 electrons around it. But everything in the third structure also has an octet. So that's good. Okay. So this middle structure is not looking good. Okay. Let's continue on. I'll put rule number 1 here. Maybe we'll do this. Rule number 1. Based on rule number 1, the first one's good, the third one is good, but the middle one is not good. If we consider rule 2, we want as few formal charges as possible. So this first structure looks great because it has 0 formal charges. These 2 structures over here, the second and the third, I'm going to put X's. Those aren't great because they have 2 charges. They have a negative and a positive, as opposed to the left, which has 0. Okay, so more points for this first structure. And then for rule number 3, remember we want negative charges on more electronegative atoms. So let's consider where our negative charges are. We have a negative charge on oxygen. We have a negative charge on oxygen. Okay, so we're not gaining anything from rule number 3. Our negative charges are just always on oxygen. So we're not even really going to consider rule 3 because we don't have any negative charge on any other atom than oxygen. And rule 4, if all things are equal, we have equal contributors. Clearly, we don't need to use that rule because we have some differences here. So our best resonance structure is this one on the left. I will put major resonance structure there, major. The one in the middle is going to be the minor resonance contributor. And the one on the right here is sort of an intermediate resonance contributor. You could also see the one on the right called the minor contributor and the one in the center called an insignificant contributor. Either way, if you're ranking them, this one on the left would be the best, number 1. The one on the right would be number 2. And the one in the middle would be number 3, the smallest contributor. Okay. So just to summarize the whole ranking system here, what we're doing is we're drawing the resonance structures that are possible. Okay, that shows us where the electrons, where those delocalized electrons could potentially be. They could be lone pairs, they could be double bonds, etc. So when we draw those resonance structures, we're showing where those electrons can be, and then we're going to rank those resonance structures based on their overall impact as to the overall electronics of the system. Okay, our most major contributors are going to be most accurately showing where those electrons are. Okay. Okay, so that's a good practice problem. If that made sense, great. If not, that's okay. There will be plenty more practice in the workshop. But for right now, we're just going to quickly cover one more tricky little topic with resonance. We're going to take a step back and consider the delocalized electrons. Now remember, resonance is all about those delocalized electrons. Those delocalized electrons are electrons that are free to move around, and they're not localized or stuck to one specific atom. So let me draw a molecule here, nitrogen, and we'll put maybe this over here. Okay, let's draw that, and we will also draw this. Now, we should be able to understand which pair of electrons, the left or the right, which nitrogen's electrons are localized and which ones are delocalized. So if we look at the structure on the left, we have our lone pair here on nitrogen. Are these electrons localized or delocalized? What we're asking is essentially, are these electrons participating in resonance or are they not participating in resonance? If they are participating in resonance, that means they're delocalized. So looking at the left, these two electrons are not participating in resonance. There's a double bond, but we have this sp3 hybridized carbon in the way. There's no resonance because we do not have an allylic lone pair. We don't have a lone pair in the allylic position adjacent to a double bond or a positive charge, right? So this lone pair is not participating in resonance, which means that those electrons are localized. Those electrons are not moving around. If we look over here, nitrogen's lone pair on the right can participate in resonance, right? We can draw a resonance structure where we put a positive charge on nitrogen and a negative charge at the end of this chain. That means that those electrons are delocalized because they are participating in resonance. Okay? Hopefully that makes sense so far based on everything we've talked about. Resonance, delocalized electrons. Okay, so with that in mind, let me draw a structure. Keep that in mind. I'm going to draw a common base called pyridine. Okay, this is a very common base in chemistry. We'll talk about acids and bases next chapter. So when I draw pyridine, you might see something. We have a nitrogen with a lone pair, and it's adjacent to a pi bond, right? There's a double bond next to a lone pair, so we should think resonance, right? Well, again, we're going to break a rule in organic chemistry, and we need to think about why. So this lone pair is actually localized which means it's not in resonance, even though it is technically adjacent to a double bond, right? We have a double bond over here on the left, and we could draw a resonance structure like this, right? Where we take that pi bond and we put it right here to make a negative charge. Those arrows look good, but in fact, they're not. And we need to remember the reason for this is that resonance is dealing with the p orbitals, right? We're dealing with the electrons in the p orbitals. So if we draw pyridine sort of two-dimensionally, if we can envision this as being a flat molecule like a pancake, right? Flat pancake molecule. We have all of these p orbitals here on all of these carbons. Okay, we have all of these p orbitals, and then we have this p orbital on nitrogen. Now, this lone pair is actually out here in an sp2 orbital. This lone pair is not in a p orbital. What is in a p orbital? It's the double bond here that's attached to nitrogen. Nitrogen has a double bond. I'll draw in red. Let's draw all these double bonds in red. Remember, these double bonds are bonding between the p orbitals of these atoms. So we have a bond here in red between nitrogen and this carbon. We have a bond between those two p orbitals, and we have a bond between these two p orbitals. Those are the delocalized electrons. We could draw arrows like this. Remember, these electrons can be in resonance. They can all kick each other over one position. But these two electrons on nitrogen are just not in a p orbital. Those are in an sp2 orbital. Okay? So this is sort of a tricky little rule. And you have to kind of think about it for a second. Are these two electrons in a p orbital? If they are in a p orbital, then they could be delocalized. They could be participating in resonance. If they're not in a p orbital, that means they're not participating in resonance. Okay? So a little rule that we could follow. When an atom has both a pi bond and a lone pair, they will not both participate in resonance. Okay? Typically just the pi bond will. Okay? So there's our little rule that we could follow. When an atom has both a pi bond and a lone pair, they can't both participate in resonance. They can't both be in a p orbital. Okay? Let's look at an example of this one more time, okay, with a different structure. Let's take this molecule here. Okay, so we have a 5-membered ring here. Nitrogen. Okay, we have a double bond at this position and this position. NH2. H. Remember, each nitrogen has a lone pair. Now, this question, let's combine a couple different things here. Let's find the geometry of each nitrogen. Let's draw some resonance structures. Draw resonance structures. And let's compare whether we have delocalized or localized electrons. Okay, let's find these three things. So looking back, thinking back to our geometry unit, let's take this nitrogen on the right. I'll do this one in red. I'll do each one in a different color. This red nitrogen here, it has 4 things attached to it. It has 2 hydrogens, it has a carbon, and it has a lone pair. So those 4 things spread out into what shape? A tetrahedron. When we consider molecular geometry, we pretend the lone pairs don't really exist. So we have this nitrogen up here with a lone pair, a carbon, a hydrogen, and a hydrogen. So these spread out in the shape of a tetrahedron, but if we ignore the lone pairs, we have a trigonal pyramidal geometry. Abbreviate it with trig-pyr, trigonal pyramidal. If we look now at this blue nitrogen, let's take this one. What is the shape of that nitrogen? Well, that nitrogen is connected to 3 things. We have a nitrogen with a lone pair, a double bond, and a single bond. So 3 things will spread out in the shape trigonal planar, all in the same plane, 120 degrees apart from each other. If we ignore the lone pair, it looks like we have a bent geometry. Okay. And then let's take green for this last nitrogen. This nitrogen is connected to how many things? It's connected to 4 different things. We have a lone pair, we have a hydrogen, we have a carbon, and we have a carbon, okay? So it looks like this might be trigonal pyramidal, right? Just like the other structure up here. It's connected to 4 things, 3 of which are bonds, 1 is a lone pair, so it should be trigonal pyramidal. But this is actually going to be trigonal planar, okay? And you might ask why that is. Well, I'm going to put trigonal planar there for now, and as we go through here, it should be more clear to you towards the end. I'm going to leave that structure there because that's the tricky one. The other geometries were just like before. Hopefully we got those, but I'm going to leave this one here for us to think about as we work through the rest of this problem. Okay, so the reason is resonance, and you'll see hopefully here as we draw resonance structures why that might be. Let's take this lone pair if we want to draw a resonance structure. Well, actually, first, let's talk about delocalized versus localized electrons. Okay, let's talk about localized versus delocalized so we know which electrons we could use for resonance. Looking at the red nitrogen, these electrons over here are clearly localized. There's no double bond in sight nearby, right? So there's really nothing we can participate in resonance. Those are localized electrons. No resonance there. Now for the 2 nitrogens in the ring, that's what we have to think about. Now this blue nitrogen, this lone pair over here is not participating in resonance because the nitrogen has a double bond on it. Remember on the previous slide when we were talking about this, if we have a double bond and a lone pair on a nitrogen or on any molecule, they can't both participate in resonance. Typically just the pi bond will. Okay. So that means this lone pair is also localized because it's in an sp2 orbital and not a p orbital. The p orbital has that pi bond in it, that double bond. So those electrons are also localized. If we look at the green nitrogen, these electrons are delocalized because they can participate in resonance. These electrons could be in a p orbital because there's no pi bond on this nitrogen. So these electrons here on the green nitrogen could be delocalized. And it looks like they will be because we have double bonds next door on both sides. Okay? So when we have the potential for resonance, the delocalization of electrons, this trigonal planar structure I'm sorry, this trigonal pyramidal structure, which we thought we would have, right? Let me draw it again over here. Carbon, carbon. This green nitrogen we thought would be trigonal pyramidal, but since we have this resonance occurring, this potential for resonance, we have this lone pair here, which if we draw the rest of the carbons, there's a double bond right next door. This lone pair will actually go into a p orbital. The geometry of this nitrogen will change, and this nitrogen will become sp2 hybridized, flat, trigonal planar, and those electrons will then go into that orthogonal p orbital and allow it to participate in resonance. Okay, so this is a tricky topic. It's a very tricky situation we have. We have this nitrogen, which appears to be trigonal pyramidal. It has 4 things bonded to it in the shape of a pyramid with a lone pair on top. But the molecule will actually change its geometry to allow this lone pair into a p orbital, into that orthogonal p orbital, like I've drawn up here, to participate in resonance with these double bonds next door. Okay. So the geometry of this green nitrogen is actually trigonal planar because when it adopts that geometry, it can participate in resonance. So that's sort of combining a lot of different topics we talked about to figure that out. That's definitely a challenge question. I wouldn't expect you to get that right off the bat. But I think it's a really good example that shows how strong of a force resonance can be. Molecules want to participate in resonance. It's a net stabilizing force. It's very good if a molecule can participate in resonance. So this molecule will adopt that conformation, which allows it to do so. Okay. So if we draw some resonance structures of this molecule, what could we do? Whoops. So we know these green electrons are delocalized electrons. Let's take them and put them into a pi bond, and we'll put this pi bond on that carbon as a negative charge. So we could draw this where we have NH. I'm going to not draw the rest of the molecules just to save time. That'll give a negative charge here. Positive charge over here. This nitrogen now has 4 bonds. We could take this negative charge and we could put it in between these 2 atoms here, and then take this pi bond and put it here as a negative charge. That would give us HN. Double bond here, negative charge here. And we could take this negative charge, put it down right here, take this pi bond, drop it off there as a negative. Okay, so that would give us this structure over here. Still have a positive charge on that nitrogen, by the way. 5-membered ring, nitrogen, negative charge here, double bond here, right? And we could take this negative charge, drop it off here, put it on this nitrogen. That's going to give us, let's see, this nitrogen is still positive because it has 4 bonds. That's going to give us this structure here. Negative charge on this nitrogen. 2 lone pairs, double bond here, right? And finally, to get back to our initial structure, we can do that. Okay, so we can move those negative charges, those double bonds, all the way around that ring system. Note that when we do it, let's take this light blue. These electrons are the ones that are delocalized. I'm highlighting in light blue, okay? These electrons are the ones that are moving around that ring system in all the cases. We have a lone pair, we have 2 pi bonds, and they're moving around. That lone pair on that nitrogen on the bottom left is not moving. It's localized. The delocalized are these ones highlighted in light blue. Those are the ones moving around the ring system, participating in resonance, that are delocalized. Okay, so all of those light blue electrons here, I'll even draw them over here. These light blue electrons are all delocalized, participating in resonance. Okay. This question was definitely a challenge question. There's a lot of resonance structures here. There's a lot of stuff going on. It's okay if you didn't fully follow along on this one. Just remember that previous rule on the slide before. Remember that if you have a double bond and a lone pair on the same atom, typically just the pi bond will be participating in resonance. That lone pair is most likely going to be localized, okay? The reason for that is because we need p orbital electrons to participate in resonance, and those electrons are simply not in a p orbital, okay? I understand that resonance is very confusing at first, can be difficult to grasp, but hopefully after the workshop, if you're still a little shaky on it, if you're shaky on this question, that's okay. This was a challenging question, but hopefully you should be comfortable with more basic structures, right? If we have a double bond next to a positive charge, if we have a double bond next to a negative charge, hopefully these basic resonance structures you can identify, draw the proper arrows, and then understand where those electrons are going, okay? Again, we'll practice this in next workshop, so hopefully by the end of that, you're feeling more comfortable. And I hope this discussion was helpful in ranking resonance structures and understanding when we have localized or delocalized electrons. Okay, see you in the next workshop, which will be workshop number 3, where we practice resonance. Take care.